We're getting a little bit of feedback there. Rasmus.
This is just the window opening.
Okay, gotcha.
Okay, when this is done.
Excellent, and it's time to begin. So I'd like to welcome everyone to our final day of training. Today we're going to have Rasmus give us a great talk here on multiphysics modeling. Is it preCICE? Is that how you use
Exactly.
preCICE coupling library? And this is a great session that's going to tell us, I think, how to link OpenFOAM with other applications out there, and I assume for multiphysics modeling purposes and multi-domain modeling. So something that we're all moving towards in an exponential rate, it seems. So without any further talking, I'll hand it over to you. Thank you.
Exactly. Thank you very much, Jonathan, and hello from Munich. We are in the OpenFOAM workshop, and we have seen already many approaches to multiphysics that usually are inside OpenFOAM. But if you are here, you may have good reasons that you want to couple OpenFOAM with other solvers, for example, deal.II or CalculiX, or even two different OpenFOAM solvers. And you may want to do this in a numerically and computationally efficient way. My name is Gerasimus Kourtakis, and I'm a doctoral candidate at the Technical University of Munich. And today I also have with me my colleague Benjamin Neukermann, who should now wave in the video.
Hello.
And he may jump in at specific points. On a few organizational notes, first of all, this is a training session, but it will be quite dense. You are not expected to try things live, but please pay attention and ask questions in the chat. At specific points, we will bring several of these questions in the session, and everything is available on GitHub, also the slides and the software, and I would very much like that this session is being recorded. Then let's jump into it. The big picture of preCICE. In partitioned multiphysics that we're doing here, we often have different solvers for the different domains. For example, we may have OpenFOAM as a fluid solver and deal.II as a structural solver. To couple these two solvers, we don't need anything else than to call the preCICE library, which is a few additional lines of code. To make our life easier, we can collect all these changes in what we call adapters, and we distribute several of these adapters to make your life easier. A good thing of this approach is that even if you don't find an adapter, you can very easily couple your own in-house solver. And if a commercial solver has a good API, we can also couple this as well. We provide adapters for OpenFOAM that I would like to discuss in detail today. As you do, there is a third-party example for FOAM extend. For structure solvers, we have many tutorials for CalculiX, and we are lately experimenting a lot with Phoenix, deal.II, and Nutils. If you want to write your own adapter, preCICE is written in C++ and has API in it, but all the major scientific computing languages are supported. Now, let's zoom into this green box in the middle, which is the library. It's one thing that every solver loads and takes care of making the two solvers or more solvers communicate. And this is done efficiently through TCP sockets or MPI. It takes care that data is mapped between different meshes. This is particularly important as you may have a very fine grid in your fluid solver, while you still have a very coarse grid in your structure solver. As a coupling library, of course, it has coupling schemes and it has a variety of them that you can choose at runtime. You can easily switch from an explicit to an implicit coupling, and I will come to these terms later. They are different than what they are used in the OpenFOAM community. And we also have very advanced acceleration methods to make the iterations between the two solvers as few as possible. A feature that is coming up soon is also time interpolation, but this is out of scope for now. This tutorial will mainly have three levels. In the beginning, we will get our hands a bit dirty and need to remember a bit of Python. This will only be so that we can use the preCICE library in two simple Python solvers. And this is only so that you understand what is happening under the hood. Hopefully, you don't need to program to couple your OpenFOAM code or most of the OpenFOAM solvers out there with other solvers. And in the beginning, we will focus in level 2 on the OpenFOAM adapter itself, how you can use it, how you can configure it. Then we will briefly talk about how to do a fluid structure interaction, coupling OpenFOAM, and deal.II. So in the first level, we will program, but in the second and third level, we will mainly use components that are already available in preCICE. Let's jump into the first level. We will need for this recipe preCICE version 2, which was released in February and brings many good updates. And it's easy to install it, for example, using binary packages for Ubuntu. Only for this example, we will need Python 3, the Python packages NumPy and Matplotlib, as well as the preCICE Python bindings. These are very easy to get, especially if you have a recent version of pip, by just doing pip3 install user preCICE. Now, let's look into our first example. We thought we could bring something easy that everybody can relate to and does not need much explanation. Therefore, we thought of this generator and propagator example. Here we have two Python scripts, and the first one, here generator, the right boundary of the domain essentially, is a 1D solver that is completely dummy as it only generates random data on its nodes. In the square on the left, we have a propagator, which simply does a convection diffusion of a completely arbitrary scheme. What it does is that it applies a 5-point stencil and propagates values from its right boundary towards the rest of the domain. Now, in this example, we will talk about the simplest coupling possible. This will be a unidirectional coupling. There will be no the generator will be passing values to the propagator, but there will be no feedback from the propagator to the generator. Therefore, the generator will just be able to continue. There will be no more synchronization than that and no more iterations for convergence. Let's briefly look into the scripts. You can see that they are very, very short. So the first one fits in one slide. What do? We import NumPy, and then we generate a mesh of 20 points. We define a time step size, in this case 0.01, and then we repeat until time 0.1. We generate some random values for u, and we increase the time. You can find these scripts together with the slides on this repository. Then we have the propagator, which is obviously a bit more elaborate. We have now a 2D solver, so we define x and y coordinates, again a 20 by 20 domain in this case. And we initialize our solution with zeros. We set the time and the time step, and we set some arbitrary boundary condition. So what we get on the right side is essentially constant in the uncoupled case. Then, again, until time 0.2, this time, we apply a 5-point stencil. And we don't need to go into the details on how this works because this is, of course, completely unphysical. Now, please excuse this technical glitch that I cannot resolve completely. So let's see how we can run these codes. We just do Python 3 and we run two solvers and they simply run. Just run them one after the other, they don't interact at all. The one reports and generating data, the other is reporting and propagating data. And this is what we would see then in the propagator case. On the right, we get some constant, essentially boundary condition, which we propagate. Not very interesting. Let's make the two solvers now talk to each other. We need to call methods of the preCICE API. All of these are documented in our documentation, but let's now look at a small set and of the basic instructions we need to add. First of all, you see that I have left some space after importing NumPy, and this is because we need to import preCICE, and in particular the preCICE Python bindings. Then we have already defined the mesh of our solver, and then we need to configure preCICE. What do we have here? We have the name of the participant. Remember, we have two participants. The one is called generator, the other is called propagator. These names, together with many other options, are defined in the preCICE configuration file, which is an XML file called preCICE-config.xml. preCICE is by default interesting and useful for parallel simulations. Therefore, it expects in its constructor the MPI communicator size and the current rank. Here, we can simply set these values to 0 and 1 as we have a serial simulation. Then, after configuring, after creating and configuring preCICE, this happens in one step in preCICE version 2, we need to define the coupling mesh. We have already defined the mesh in the configuration file, which we call generator mesh. And to make our life easier, we don't work with names, but with IDs, some integers that stay the same through the simulation. Therefore, we ask for the mesh ID of generator mesh from preCICE. That is called interface. Then we need to actually define the coupling mesh on the boundary of our domain, which is the same nodes that we are using. Then, after we set the mesh vertices for this mesh, it's time to initialize and finalize preCICE. In the initialization, the two participants find each other and exchange some first information. And in the finalize, all the communication channels are destroyed. Let me mention here that preCICE is completely parallel and peer-to-peer. So every process of every solver would normally need to establish communication channels with the respective process of the other participant. Now, after we initialize and finalize, we also want to do something in every time step. So after every solution time step that we have in our transient loop, we want to also advance the coupling for this time step. This method expects the time step size as an input. And after calling it, we can also give the control of the end of the simulation to preCICE. So you see now in our while condition, we have is coupling ongoing. Then, apart from only controlling the end of the simulation, we can also let preCICE control the time step. And this is because in sometimes the two solvers may not be able to proceed as long as they want because a coupling time is approaching. Therefore, we need to take the minimum of the time step that preCICE wants us to do and the time step size that the solver wants to do. So we need to be able to override the time step of the solver. And this is also returned at initialization. Now, we're not completely there yet. First of all, we need to do the same things in the propagator. I would like you to do this at home. And you can also find the solution in the repository. I will not tell you directly where to find it now. And let's see what's happening when we run it and how can we actually run it. So here I will use Tmux to split my terminal in two, as it's very convenient when we have two solvers at the same time. We are starting here the two solvers completely normally. There is nothing in the middle. There's no server or anything that we need to start. You see that the generator starts, reports some information about preCICE, finds the configuration file, and then it waits for the coupling partner to appear. Now, let's also start our coupling partner propagator. The moment it starts, we see that the simulation starts. Notice that on the left side, the generator has essentially completed and waits for the propagator to also complete, because remember that we have a one-way coupling. But still, even though we call advance, nothing is happening. So yes, the solvers interacted, but they did not exchange any data. So did we forget anything? Yes. So apart from defining a mesh and defining vertices for this mesh, we actually need to associate data with these vertices and this mesh. Therefore, after we set the mesh vertices, we can also get an ID for the data that we're exchanging with a lot of imagination. In this example, we're calling data. And we can now refer to it. And we can call, for example, the method write block scalar data to write a bunch of data, a bunch of scalars of data ID to the vertex IDs. And what we write is the solution view. Then we also have the advance, and only then, and not before that, this data will be sent to the other participant. If we had a bidirectional coupling, then we could also call similarly read block scalar data to read values back. Apart from scalars, we can also exchange vectors, and there's also a way to exchange only one piece of data at a time. So now it should actually work. Let's see what's happening. Now, we run the solvers the same way, but this time just for change, let's start the propagator first. So the order does not matter at all. And the simulation starts. We see exactly the same picture as before. We wait until it finishes. And let's jump directly to the results. Now you see something more interesting. The propagator changes its boundary values, its boundary condition, every few time steps. Notice that we here, for demonstration, we don't couple every time step. We also don't need to couple every time step, but we couple only every few time steps. Therefore, this is also quite important. The two solvers can do completely different time steps. We may have a fluid simulation that does very small time steps and a structure simulation that does very large time steps. And then we only couple every few time steps of the one solver. Again, let me state again here that this is the simplest case possible that we can imagine. So this is a unidirectional, serial, and explicit coupling with a nearest neighbor mapping, where we actually even have meshes of the same number of nodes. Let me clarify two terms here. So what I just now explained, we refer to as subcycling. So the one solver is doing multiple time steps per coupling time window of preCICE. And we also distinguish between explicit coupling, that is when the solvers interact only once, or implicit coupling in our terminology. That means that the solvers iterate until they reach convergence. In that case, we would also need to return the solver to a previous state, for example, by storing and reloading a checkpoint. Now, I talked about many things that are defined in a configuration file of preCICE. Let's do a short attempt to look into this file. And I will start not by looking at the file, but by visualizing the file. Since a few months, we have a very nice config visualizer, a tool that can parse a preCICE config file and make a graph out of it. And here we can see that we have the two participants, the generator and the propagator, also declared by these polygons. And these two are coupled in a serial explicit scheme, with the first participant being the generator and the second participant being the propagator. They communicate through sockets, and let's now see the flow of data. The generator is writing something that is called data on its generator mesh that it defines, therefore we have it with solid line. And the propagator reads this data from the propagator mesh. So how do we go from this generator mesh to this propagator mesh? We first exchange the generator mesh from the generator to the propagator, and then the propagator does a nearest neighbor mapping from the generator mesh to the propagator mesh. This is also something that can help the performance if we have different number of cores in the two sides, and the participant with the many cores can actually do the mapping in a smaller number of data. Then let's look at the exact file, which describes the same thing. First of all, we have here a 2D solver interface. Then we are only defining data as scalar. And then we have two meshes, the generator mesh and the propagator mesh. Both are using the data that we defined above. And then we define the two participants. First, we define the generator, which uses the mesh, generator mesh, which actually it also provides. So it's the one defining it. And it writes data onto the generator mesh. There's no mapping or anything else defined here. But if we look at the propagator, we see that here we have, we read data from the propagator mesh, and we actually map from the generator mesh to the propagator mesh, and we do a consistent mapping. An alternative would be a conservative mapping. This is reading from the generator mesh to the propagator mesh, and because we need both meshes here, we need to also use them above. Now, in the we can also define how they communicate. For example, here with sockets. An alternative would be with MPI. And we also define the coupling scheme, which is now serial explicit. The first participant is the generator, the second is the propagator, and we couple every 0.01 seconds. The maximum time when the preCICE will say the simulation should now stop is 0.1. And we also define that we exchange the generator mesh carrying data from the generator to the propagator. Now it's the time that I can drink some water and I can ask Benjamin for any questions.
Yes, there have already been a few questions in the chat. I'm trying to answering them. Please feel free to ask more. I guess so far we were pretty fast, so maybe we left out some things. Otherwise, I think we're doing good, and I would hand back to Marquis.
Okay, then I assume we can continue. We are kind of ahead of schedule, and this is okay because we will have a lot of this time for proper discussion at the end. So let's now see how we can use the OpenFOAM adapter so that we don't have to program all these things in OpenFOAM. We have done this for you. It's a project that is growing more and more and have contributions from many people. And all these are not only for features, but also to make your lives easier. So what does this adapter do? First of all, it's a function object. Therefore, you don't need to change any code inside your solver. It only needs to support function objects. And the adapter will then link to preCICE. It needs to be able to override boundary values of OpenFOAM with values it receives from the other solver through preCICE. And we define preCICE buffers that we read and write from. And of course, it needs to do the opposite. It needs to be able to extract boundary values from OpenFOAM and pass them to the buffers of preCICE. Then, in implicit coupling, we need to redo some iterations. So when preCICE says so, the adapter should be able to get a complete checkpoint of OpenFOAM, including time, and then tell OpenFOAM, okay, now you need to revert everything back to the previous state. Then, sometimes the two solvers need to synchronize. So if preCICE tells that the maximum time step size is actually smaller than the one that OpenFOAM wants to do, then the adapter should be able to adjust the time step size of preCICE, of OpenFOAM. For this recipe, we will need preCICE version 2, installed the same way, and a recent OpenFOAM version. So we try to support as many as possible. We currently support all the latest versions of the ESI and the foundation. We unfortunately cannot out of the box support foam extend for technical reasons, but I would be very happy to accommodate contributions. And we also need the preCICE OpenFOAM adapter. If you get the latest master, it should work with all the ESI versions and the foundation versions up to 5. But in the next days, I'm going to merge a pull request that is going to treat everything the same without you needing to do anything else. You can find detailed instructions in the wiki of the adapter. Then, how to build this? It's very simple and very automatic. We have an old wmake script, which simply calls wmake after defining a few environment variables. And to help you find out what goes wrong, if it goes, and the files that you need to send us if you want to debug something would be the old wmake.log. So the same screen output that old wmake shows. wmake.log, the output of essentially make, and ldd.log, which checks if the libraries can link at runtime. I'm not going to show you the details of how to build it. It's very simple. Simply click on this when you access the slides. Now, let's look at the tutorial that is distributed with the adapter. Most of our tutorials are distributed separately. This is with the adapter. And this is a conjugate heat transfer scenario where we have a channel flow with buoyant pimple foam. And below it, we have a heated plate solved with Laplacian foam. In the channel, we have an inlet of 300 Kelvin. And in the bottom of the plate, we have a higher temperature of 310 Kelvin. And of course, as time passes, we should see that heat propagates from the bottom to the channel, and we get these isothermal lines. Let's see what we need to configure to make this case run. Apart from the channel flow with buoyant pimple foam and the plate with Laplacian foam, we need the OpenFOAM adapter, which is exactly the same in both cases, and preCICE, which is also exactly the same in both cases. For its adapter, for the adapter for its case, we will need a configuration file, which is now an OpenFOAM dictionary. And in the middle, we also have preCICE that has this XML file that contains all the coupling configuration for both participants. Note here that if you are looking at older tutorials, this OpenFOAM adapter config used to be a YAML file, that this has recently changed. Now, let's look at the case as we download it from, as we get it from GitHub. Here we have the usual OpenFOAM files plus a few helpful scripts to run or clean our files. We have a fluid case defined normally with initial conditions, boundary conditions. We have our constants and the system directory. In the system directory, we have an additional file called preCICE-dict, which I will describe next. And we have a very similar situation in the solid. Apart from this, we also have the preCICE config.xml, which is in the parent directory of the two cases. Here we will mainly discuss, or we mainly need to change the temperature configuration file to set compatible boundary condition types that we can override. We need to enable the adapter in the control dict. We need to configure the adapter in the preCICE-dict, and we need to prepare a preCICE config XML. The case is already configured, and I will just show you the important bits. To enable the adapter, we need to go in the control dict of both cases and do exactly the same thing. This is why it is cut on the right, because it's essentially exactly the same file. So we need to go and define a functions node to define a function object. We name it arbitrarily preCICE adapter, and it is of type preCICE adapter function object, which we have already compiled, and it should be somewhere in our libraries, user libraries of OpenFOAM. Then we say that for this function object, we need actually to link to this library. Now, let's look at the configuration file of the adapter. This is short and mainly needs to say how the adapter needs to interact with OpenFOAM. First of all, it points to the preCICE config that we are using for our couple simulation, and then it defines the name of the participant. So we need to know that this is the fluid participant. It could be something completely different. This needs to be defined in the config. Then, in the adapter, we have different modules providing different coupling data readers and writers. And one of them is conjugate heat transfer, the CHT module that can read and write temperature, heat flux, sink temperature, and heat transfer coefficient. Then we see that in the solid side, we do exactly the same. We point to the same configuration file, we have the solid participant, and we again use the conjugate heat transfer module. Then we define an interface, a coupling interface in both participants. In the fluid participant, we say that our interface uses the fluid mesh of preCICE and associates it with the interface patch of OpenFOAM. Then on this patch, we want to read heat flux and we want to write temperature. We see the reverse situation in the solid, where we read temperature and write heat flux. And we do this, of course, on the solid mesh, on the, again, patch that is happened to be named interface. This can be completely arbitrary. And what this is a completely normal wall, which we define in our block mesh tick, nothing special here. Then, in the temperature file that we are coupling, we need to define a compatible boundary condition for this interface patch. Remember that in fluid, we are reading heat flux. This means that preCICE needs to set the gradient of the temperature. Therefore, we need to select that this is of type fixed gradient, otherwise we'll not be able to assign values to it. And then we give an arbitrary value which will be overwritten. Similarly, for the solid, remember that we are reading temperature, so we need to set that this is a fixed value, and again we set an arbitrary value. Let's look at the preCICE config XML, which starts getting a bit more real life. This time we have a 3D interface, and we have two data, the temperature and heat flux, and both are scalars. Then we have the two meshes, the fluid mesh and the solid mesh, and both use the same data. Let's then look at the fluid participant. We have here, again, a mapping from the solid mesh to fluid mesh, and this is again consistent. And we write temperature and we read heat flux. And of course, we need to use both meshes in this participant to be able to map from the one to the other. Exactly the same situation in the solid that also does a mapping to keep our simulation balanced. And then we go directly to the coupling scheme node. Here we see that we are using a serial implicit scheme. And this means that now that we have a bidirectional coupling, the solid executes, then sends values to the fluid, and it waits. Then the fluid computes, passes values back to the solid, and waits. And then if the values on the interface have not converged, which usually does not happen in the first time step, we execute this again by going back in time. So this is an implicit coupling. And because the two participants wait for each other, this is a serial coupling. We could also have a parallel explicit or parallel implicit scheme where, similar to a Jacobi fashion, the two solvers would just communicate once and then compute the same time step at the same time, and then communicate again. Now, what do we have here? We have again the coupling window size and the maximum time step. Then we define the order of the participants. The first is the fluid and the second is the solid. And we exchange temperature from fluid to solid over the fluid mesh, and heat flux from solid to fluid over the solid mesh. Then we have to define some criteria for convergence. So we check the temperature on the fluid mesh, and we want this to be less than 10 to the minus 6. And we have a stopping criterion for 200 iterations. So if this is hit, we simply move on. However, this should not happen, and especially should not happen later in the simulation, as we are using the interface quasi-Newton acceleration method, which can learn from the history of a simulation. How to configure this would be a complete separate discussion, and maybe we can treat this in the discussion round. Again, this may look difficult, especially if we're preparing it and we are trying to find a bug. So we can again visualize it using the same tool. It may look a bit spaghetti, but we can follow again the same way. So fluid is writing temperature to the fluid mesh, which is exchanged and sent to the solid participant, which maps from the fluid mesh to the solid mesh and reads temperature from there. Now, let's see what happens if this runs and how to actually run this. Let's see, this is what we have. Again, what I showed you in the files. And then we go to our fluid directory and we prepare our fluid simulation completely normally. And then it's important that we go back to the parent directory and we start the simulation from there, where the preCICE config is also. You will see quite some output here. This is mostly debug output that you can switch off. And you can see that here we are running, for example, in one processor. Then let's continue to the solid solver, which we again prepare completely normally. And we can also run it. So we can run Laplacian foam again from the same directory so that the two solvers can find each other. And normally, if you execute it locally, you will get quite some output quite frequently, and this appears less frequent due to the recording. At the end of the simulation, we will also get some performance data, and you can also find all the events and so on in files that preCICE writes. Let's now see the results. We have the two cases which we need to load in ParaView. So we load our case files, and then we also load the solid case, and then we can couple this to, we can group these two, we can make a slice, and if we have results, we can visualize the temperature and see how this evolves. Let's also make a contour plot of temperature from 300 to 310 every 1 Kelvin, and this is what we get. And here let me comment that if you're using the ESI version, there is incompatibility with their implementation of the function objects, and you may get some empty result directories which you can simply remove with the script that we have there. This is a completely simple visualization issue. Then we have reached the end of level 2. So this was now how to couple two OpenFOAM solvers, and we have seen how to configure the OpenFOAM adapter and how to configure a more real-life simulation for conjugate heat transfer. Now, I would like again to drink some water and ask Benjamin for questions.
Hey, yes, questions are piling up, but questions are mainly about preCICE in general. So I'm not sure if it makes sense to raise them here for everyone. So they're not targeted so much for the training, the tutorial that you just showed, but more general about features of preCICE.
Okay, then
This is Jonathan.
then I will speed this up a bit so that we have more time for discussion at the end. And please collect the questions that may affect most of the people. Is there anything regarding the configuration of OpenFOAM?
Of OpenFOAM, no. There were some questions about the configuration of preCICE, but also more in a general sense, not specific for the example here.
Okay. Then
maybe one thing, if you ask questions, please ask in the public chat and don't send private messages. Also, Zoom does not handle private messages so well, so I always have to switch back between public and private. Please ask on the public chat.
Also, feel free to ask, especially later, if we don't have time to discuss everything. Please ask on the conference application, or the best place if you have more elaborate questions would be at our preCICE forum on this course that I will show you at the end. But it looks like we have more than enough time to complete the puzzle and see how can we actually couple OpenFOAM with a completely external solver that OpenFOAM has no idea about. Let's jump into it. We have several tutorials that you can find on our website. Most of them are available on the tutorials repository, apart from the one that I just showed, that for historical reasons is in the same repository as the OpenFOAM adapter. And this is an overview of what we have. So we have conjugate heat transfer tutorials, FSI tutorials, some coupled heat equation and structure-structures coupling, and solvers you can see are various OpenFOAM solvers. We have CalculiX, we have Phoenix, Nutils, that is another finite element library, and deal.II, as well as FU2. Now, we already discussed the first one, the Borean pimple foam Laplacian form flow over plate. Let's now go to the FSI cases. I would like to discuss the OpenFOAM deal.II case that you may be familiar with. Is a channel flow with a vertical perpendicular flap attached to the bottom, which due to the flow, it starts bending. This will oscillate for a few time steps until eventually it reaches some kind of steady state. You can find detailed instructions for this in our wiki in this link, but let's see how it would be if you run it. For this recipe, we will need preCICE version 2. There is a catch here. You need to also have preCICE built with PETSI, but only if you want to run the case in parallel and with RBF mapping. And I will explain both later. If you're using Ubuntu 20.04, you can simply get the Ubuntu package that we have for preCICE version 2. It's built with PETSI. And in a later release, you will not even need PETSI to run this in parallel in a single node. Then you need again OpenFOAM, a recent version, the latest OpenFOAM adapter. We will use deal.II 9.2. and the deal.II adapter that we have. If you don't know, deal.II is similar to OpenFOAM in the sense that it provides libraries and methods that you can use to build your own solver. It has some examples prepared, and we have derived from one of these examples to make our own nonlinear and our own nonlinear solid solver in deal.II that is a completely toy solver to show how one could use it. And our adapter is nothing more than such an example of a solver. Then, let's configure again OpenFOAM. This time we need to configure not the temperature, but the velocity of the flap. And this we need to set to a type moving wall velocity, again with an arbitrary value. And we need to set again a boundary condition type for the point displacement, as we are gonna read displacements from the other solver. And for the mesh motion, we are using displacement Laplacian. To configure the OpenFOAM adapter, we have again this system preCICE dict. And what is different here, this time we are using the FSI module, and we define two interfaces, interface 1 and interface 2. In interface 1, we have a mesh defined on the face centers of the flap patch, and it's called fluid mesh centers in preCICE. And there we want to write stresses, and we don't need to read anything. The interface 2 is defined on the face nodes of the flap patch, and we name it fluid mesh nodes. There we read the displacements, but we don't write anything. Here we may also read some additional parameters. We have an incompressible solver, so we read the reference density. For the deal.II adapter, I'm not going to go into detail. You can find everything in the deal.II adapter wiki, but I'm only going to say that we are going to use the linear elasticity solver, and this uses a linear elasticity.prm configuration file that has several subsections and sections, and there we have a subsection for preCICE. Here you can again see that we have the preCICE config XML, we have that this participant is named solid, and that we read stresses and write displacement, so the reverse. Let's now configure preCICE. I will skip to the interesting parts. So we have the fluid, which reads displacements and writes stresses. But this time we have a more interesting second order mapping technique with radial basis functions, in particular thin plate splines. And this is a read mapping from the solid mesh to the fluid mesh nodes. And it's a consistent mapping, as we are only mapping stresses and displacements here. We do the same for solid. And just for the demonstration, I want to show you a nice feature. You can also define a watch point on a preCICE mesh, which will plot you the values of the data that this mesh carries over time. Here we define this watch point to be on the tip of the flap. Other features that you can use is also to export the complete meshes and see how the mapping works, but I'm not going to discuss this today. Then we are using again interface quasi-Newton, and let's see what's happening. We are now inside the tutorial directory. We have the same tree. And for the sake of presentation, I have reduced the time to 0.005. This is mostly for the recording, as I cannot upload larger files. Then you see that we have a run fluid and the run solid script. And for example, the run solid can simply take an option for the linear or the nonlinear solver, and then normally call the linear or the nonlinear elasticity solver with the parameter file. It does nothing else. Let's also see the run fluid file, which prepares and runs the case normally. And if we pass the parallel flag, it can run the case in parallel, decomposing, running MPI run with MPI run, and reconstructing it. Now, excuse me for the technicalities, let's let it run. You see again the run solid file. And you can simply run the fluid in parallel. We see here that it started with 4 processes. And we also run the linear elasticity solver. We see they normally communicate the exchange data. And after a while, and a few iterations per time step, they end. Now, let's look in some of the files that preCICE exports. And this is, for example, the iterations that the fluid takes. And we can see that it takes more or less, after a while, 3 iterations of its own time set to complete. And the solid also takes, after the first iteration, takes 3 times to complete. Then let's also see the results in ParaView. We load again the fluid and the solid. Unfortunately, the 2 solvers define a different define time in a different scheme. So we can load both cases, but we will not be able to see them synchronized. If you know a good trick for this, I would be very happy to find out. So we see that the flap moves, and notice here that we have a solid model. So you see a linear solid model. So you see this skewness of the flap. If you run the nonlinear variant, you should see a much better behavior. Finally, let's try to plot the watch point that we defined. We can do it in our favorite plotting tool. A very simple choice would be GNU-plot. And if you run the script, which is also provided with a case, you can see how the flap moves. And this is a very helpful tool for validating your results. Then we also have a recording of how the same case would be with OpenFOAM and CalculiX, but it would again going through the same case and seeing more or less the same thing. So you can watch it at home or run the tutorial. Now I will go also to the tail of the presentation, and we will have all the questions later. When you want to start, you will probably go to our website. Of course, this is not as often updated as our GitHub, where we do all the daily development, but it has all the information that you need to get started. So mainly you can go to the resources to see what I will show you now. You can go to testimonials to see what other people are doing with preCICE. You can go to publications to see recent things we did, and you can find more about the history of preCICE and who we are. All the documentation is currently in our GitHub wiki. This has been very nice until now because we can easily edit it. And as now the content has grown quite a lot, we plan to merge this with our website and make the website the main portal that you will need. You can find here different ways to get preCICE. For example, you can find how to get preCICE with SPAC if you want to install it on a supercomputer that may have limited dependencies already available. You can find packages for Ubuntu or for Arch, and so on. You can find all the tutorials. You can find the configuration options for all the things that I showed you in the preCICE config. And you can find some literature guide if you click on this link, if you want to learn more, and all of our tutorials. Then eventually you will have questions. We can discuss many of them now, but you may have, first of all, the question is preCICE for me. So then you can simply go to this category in our preCICE forum on this course, and you can ask a question there. If you have questions on how to use preCICE or anything, you can also do it there. This exists for like 9 months now, and it's already quite active. So we would also like, after you start using preCICE a lot, to also try to contribute with answering questions. We would really need this. Then if you want to ask something quicker, you can find us where we also daily communicate for all of our development needs. This is on Gitter, and we have a room that you can ask any question, the lobby. But please, if something is could be helpful for future readers, please keep it on the forum. Then, since February and our first preCICE workshop, we have now more active YouTube channel where you can find the recordings from the talks. You will hopefully be able to find this talk later there, as well as different talks. For example, my talk in last year's FOSDEM or other videos of users that have used preCICE. If you also upload results, we would be very happy to link to your video. If you're using Twitter, that I think the OpenFOAM community uses quite a lot, you can follow us. And if you prefer the more traditional way, there is also a mailing list that is not very spammy. So you could expect 1 email per month or so about news of preCICE. Finally, I would really like to invite you and hopefully to meet you in person in our second preCICE workshop, which this time will be at the University of Stuttgart in Germany, and 99% sure that it is going to be in February 22 to 25. And you can meet me, Benjamin, and hopefully many of the people that came to our first workshop in February. This contributes the presentation, which was mixed with the implementation part. I would like to thank you very much for being here. And let me tell you that here it was only me and Benjamin, but there are many, many people that have contributed a lot. For the OpenFOAM adapter, I also need to thank Lucia Zung, Derek Riseu, David Schneider, Julian Seufert, and many more people. And please feel free to start a discussion on our forum. And you can get this presentation from GitHub. So thank you very much. And I would like now to open the stage for questions about the training and more general about preCICE. And maybe Benjamin can start with the moderation.
Okay. Yeah, I'm very happy about all the questions that you ask in the chat. I did not manage to listen to your talk much, Marcus. I had to answer all the questions. Maybe two things are interesting for a broader audience, so I want to pick them up. And then we can also, of course, answer to more questions. The first one was many people were interested in how this works on a cluster. Do you want to answer, Marcus?
So can you make the discussion more concrete, or should I go the direction that can cover probably most?
Yeah, so how would you start a coupled simulation on a cluster? And can you use different number of processors and things like this?
Yes. So first of all, let's start from the communication. Let me tell you a technicality here. I told you that you need to start both simulations from the same directory. This is because on this directory, only on the initialization phase, you will see a small file, or actually now for performance reasons, a series of directories being written, which contain only a small piece of information. And this is the IP address of the other process of the other participant. This means that you can essentially run the two participants in any two systems that can communicate through the network or through the same MPI communicator. You can have the different ranks of the participants, the one running on a cluster and the other running on a workstation, if the cluster allows this. You can have the two participants starting in two different Docker containers that are apart from anything else isolated. This we use for our system tests, where we check all of our tutorials with every commit. Then on the technicalities how to start it, we actually have in our wiki, we have examples on how to start how to start a parallel simulation in several clusters and supercomputers we are working with. For example, a SuperMOOC and G here in Munich in Garching, and you can copy from that. You can, of course, start everything in the same node. Just execute a script where you start the one participant and you keep it in the background, and then you start the other. Or you can have a more elaborate job script.
Yes, and maybe to add, so when you normally you would write one job script for your scheduler, and in there you would, well, let's say you have 3 nodes, and then you would start the first solver on the first 2 nodes, and the second solver on the third node. How to do this? Of course, this depends on your supercomputer. So how to pin those processes. But then first the adapter is a library, right? So then your 2 solvers first call the adapter. So here the OpenFOAM adapter, and then the OpenFOAM adapter calls preCICE, which again is a library. So you don't need to worry about on which processes preCICE runs, right? preCICE runs on the same processes, same ranks that your solver also runs on. It's just a library that you call.
Exactly. So also, if you can go further from one node, this depends on your solver. OpenFOAM can, so the coupled simulation also will be able to.
Yes. So there are a few more questions that I think I want to pick up. I start with the last one because it fits a bit better here. What is the coupling overhead when running in parallel? Yeah, so we have tested this a lot. So this was one of the most important directions of development in the last 5 years, was to make preCICE fast. So I would say in general, the coupling should be much cheaper than whatever your solver does, so that you should not feel it. Also not when you try to scale up. So we also had this running for 10,000s of MPI ranks, and there still the coupling was not very visible. Of course, when you do this implicit coupling, so when you subiterate, you have to redo a time step multiple times for a solver, right? So this makes the couple problem more expensive than the single physics problem. I hope that I answered this question, Kenny. Maybe then let's pick up the second last one. So Joel was asking about, can you explain a little bit more the XML file, for instance, for the level 2 case? I think we still have time, so we could go back there. And John just asked, is the coupling peer-to-peer? Yes, it is. So it's fully parallel and peer-to-peer.
So is there some specific thing we should discuss about the config file? So maybe I can start this time from the visualization. Maybe this makes things easier. Or should we look deeper into the details?
Yes, Joel, if you want to give more details. If not, I would say just the big picture again. Yeah, he says, yes, that is okay, meaning, I guess, the visualization.
Okay, then let's take it from here. We have 2 participants. By the way, we can also have 3 participants if this makes things easier, which I don't think so. And we have here fluid and solid. Also the rectangles. So we have the 2 participants communicating via the network, via sockets. And we also have a coupling scheme that is serial, implicit, with the first being the fluid and the second being the solid. Then we have the solid. So the first is the fluid, so let's start from the fluid. What does the fluid do? It writes temperature to the fluid mesh, which it provides. Then it exchanges, it sends a copy of the mesh to the solid. And in a parallel case, it will only send what the other process actually needs. So it gets a copy of the fluid mesh, and then it does a nearest neighbor, could be nearest projection, could be RBF, to map from the fluid mesh to the solid mesh. And then from that mesh, it reads the temperature. And we need the mapping because they can be in different locations, different nodes, and so on. They don't even need to be fitting. Then, after it reads temperature, it solves. The fluid is still waiting, and then it writes heat flux to the solid mesh, which is then sent to the fluid. And the fluid then has all the information to do a nearest neighbor mapping from the solid mesh to the fluid mesh and read the heat flux again. Other than that, maybe we could go to specific details.
Okay. I would say, Joel, if you have, yeah. Yes, he says, I guess I can get more on the documentation. Yes, so on GitHub, preCICE, then you go to the wiki, and there's a complete section that gives a broad overview of the configuration. I'll post a link in a minute.
Yes.
And
if we finish with the slides, I could also show a few of these things. Let's collect them, and I can show them later.
Yeah. Let's first pick up another question by Brent. He was asking what are advantages and concerning also performance of sockets versus MPI communication. Maybe should I
Yes,
take this
so
or?
yes, sir.
Sorry.
So yeah, take it.
Yeah, I think there are two sides to this. So the first one is performance. We have seen that MPI can be faster than our TCP/IP implementation, but this depends on the MPI implementation, and this is really minimal. So you will only feel this if you do very large simulations. I would say for normal cases, you don't feel any difference performance-wise. And the other side to this is that yeah, we have seen that TCP/IP sockets are just much more robust on various systems, robust in terms of building. So that's why we typically recommend to use TCP/IP sockets, because normally they just work out of the box. And with MPI, well, we use very specific features of MPI. So we need these ports in MPI, and those are not always very well implemented depending on the MPI implementation. So we have seen already many problems there on different clusters. Yeah, bottom line, sockets because they're more robust and they're not much slower.
Also, let me briefly mention that one of our really main focus is to make preCICE more usable and more user-friendly, and to build a community. So we try to give good defaults that work on a laptop and so on. We know that if you are experienced enough to try to squeeze the performance, you will look for the more advanced settings, but it should, of course, work out of the box.
Yeah. Okay, there's another question. Interesting training, thank you. We run 120 million cell external aerodynamics runs and would like to do an FSI coupling to predict deformation of plastic parts. Do you think this is achievable with preCICE? So 120 million cells in the fluid code, I guess, and then you have another solid solver. I would say this is the perfect use case for preCICE, yes. So it should not be too big. We had similar large cases. So your fluid solver here is OpenFOAM, or? Okay, 120 million elements. Okay, so elements I think should still work. Of course, depends on what numerical scheme you then use and how many degrees of freedom this is. Okay, he says OpenFOAM.
But
Yes.
if OpenFOAM scales, then preCICE should not really be the problem, because we're only exchanging a small set of the domain. We are only exchanging parts of the interface, and we are doing it peer-to-peer.
And he's saying probably linked with LS-DYNA. So there were already users before that coupled to LS-DYNA. There is not really an adapter for LS-DYNA, but there is already a brief documentation online on how to couple with LS-DYNA that you could start from.
And of course, if you want to build up on this, it would be very nice to contribute it. Until now,
Yes.
we mostly did not have this for difficulties with the license compatibility. Not of preCICE, but of LS9.
Yeah, and the was a company who did this adapter, and they were not allowed to share the code, but they were allowed to share the documentation.
preCICE is LGPL, meaning that you can link to it even from commercial solvers. But other than that, it's completely normal GPL.
Okay, I don't see any current question here. It could be that I just overlooked any question before. If that's the case, please just ask again. Otherwise, we could make use of the time and maybe stepping to GitHub and showing the documentation.
Yes, so for this, let's find this. I'm not on my browser. So if you go to resources, or if you click directly on the site, you get to GitHub and you get to preCICE. This is the main repository that is also pinned here. Then, if you go to Wiki, which you can also find directly from the resources, you have several things here. So we have a link, for example, to an older reference paper we had. We are in the process of updating this. We have a literature guide for the different features, and also a roadmap of things that are probably coming up in the near future. Then you can find all the ways we have to get preCICE. And here you can see with the stars what usually works or people have experience with. Then we have the different tutorials, which you can also find on the website. Then we have the different configuration. So, for example, let's open the acceleration configuration, which is usually more complicated. So we have different acceleration techniques. We have constant under relaxation. We have Aitken under relaxation, and we have, of course, the interface quasi-Newton with different variants, different filters. So you can see here some example, and something that is even more helpful. If you go back, you can find something that we should probably link somewhere, the XML reference, which you can generate also locally as a markdown file, for example, like this. And then you can get detailed instructions on what are the possible options for every part of the configuration. The page is quite huge. I hope it renders in your browser. Otherwise, you can produce it and see it locally. What else can we see here? We have some additional tools. For example, this visualizer that I mentioned, which is in a different repository inside preCICE. We also have some common troubleshooting instructions, and we have the most useful thing for people that want to write their own adapter, which is an adapter example. Here you can find detailed explanations of all the steps I presented in level 1. And if you want to find an API documentation similar to the one OpenFOAM has, we have a doc-citizen guide. We have some dummy solvers that we are mainly using to test if the installation is correct and so on. We have more details regarding the non-C++ APIs, for example, for Fortran, for Python, for MATLAB, and how they are connected together. At the moment, the documentation is, of course, a bit mixed between user and developer documentation, and we plan to design this better in the near future. Then, if you have already used preCICE in the past, and you may have heard the news that we have a new version, there is an upgrade guide for going from preCICE 1 to 2. You need to change very few things in the configuration, and we have an unwritten promise that we will have major versions only very few years, every few years, for example, 2 or 3, so that you can focus on coupling and not in keeping up with our updates. Other than that, the project is very actively developed in Munich, in Stuttgart, and with Benjamin in Eindhoven. And we plan a next feature release, most probably for July. Then we also have some theory, and then Benjamin, what?
Yeah, maybe you can quickly show this course again.
Yes.
Just yeah. So this is probably.
Shall I go to resources?
Yeah.
I can go to this course, and you can find, for example, a user that is currently trying to make his couple amidine and OpenFOAM simulation converge. This is a thread, and you can use different tags and so on. Let's see what other resources we have. We have the chat room. We also have a few things on ResearchGate, but we don't update it so often. Here are a few of the main tutorials. And in the couple codes, you can find the not always completely up-to-date list of what we currently support out of the box. Some frequently asked questions also on this course. You may be interested to particularly look into this. For example, can preCICE be used for volume coupling? Yes, it was not designed for this. It was mainly designed for surface coupling, but there is nothing stopping you from doing it, and a few users have already successfully tried it. Then we have testimonials. So if you do a nice simulation with preCICE, we would be very, very happy to, if you contacted us and we add your story here, some selected publication, the story of preCICE, which starts essentially in the early 2000s, and then the current development team, other contributors, and the previous workshop page.
Marcus, there's another question in the chat.
Yes.
When do you think the Elmer adapter will be available? So I already answered before that this is on our roadmap. Yeah, this is a bit hard to say. So we have not yet started with the Elmer adapter development, but this is something we want to do. So this is definitely not something that will be ready in 2 months, but will take a little bit longer. But of course, we are very open here for any contributions, right? So if you are interested in coupling Elmer, we are also there to help you developing it. Yeah, so far we just noticed that we get contacted a lot about Elmar, and we decided, okay, this will be an important strategic goal to have an adapter for Elmar. Yeah.
Finally, let me
Yes.
click again on the link of the slides. I actually just showed the slides from here, so you already have the state that I uploaded. I will try to also contribute a PDF to the proceedings, but this may take some time to make the interactive parts in a static way.
Yes, I think the time is up.
Yeah, and I'll say the slides to contribute, even just a link to the slides here that we could put on the proceedings website would be great. So we can just link to that if the presentation is better hosted somewhere else. So again, I really want to thank both of you for this really excellent training session. This is very, very informative. So I'm glad to see all the people who participated, all the great questions. It's really great when the training is interactive, and we kind of lose that a little bit when we're not all in the same room, but I think here we really saw everybody actively participating. So that was really great. But we will reconvene and in about 14 minutes with our final technical sessions of the day, and use that to close out the third day of the workshop. So again, thank you everyone. Thank you to our trainers, and we'll see you all shortly in the next sessions.
Thank you very much. It was a pleasure being here.
Thank you. Bye now.
Ciao.
Bye-bye.
Have a good day.